Okay, we are recording. All right, now, first, I want to mention that at the end of last class, I've done this one example about classical versus weak solutions. And I'll just bring that back. So.
Hey, Dr. Lambers, we can't quite see everything on the board. You need to shift it that way a little bit.
Okay, is it a glare or because?
No, like the screen's cutting it off.
We just can't see like the first part of classical.
That's really weird because I'm looking at what my webcam can see, and it's showing that entire part of a board.
I promise you, we can't see all of classical. I swear.
I'm sorry. This is upsetting me because I feel like it's deceiving me. So now I don't know what to do.
Could it be because for me it's like split screen? Like I see Rachel and you.
Oh.
Let's try that real quick.
Yeah, because it should be viewing in the split screen mode anyway.
Exit full screen, and then I want to spotlight. There we go. Yep, that fixed it.
Okay.
Right click on his screen, Chandler, and click spotlight, and that will make the screen big.
Yeah, it fixed it for me as well.
Yeah. Okay, I'm sorry to be a pain. It's just that if I'm seeing one thing and you guys are seeing another, I can't have that. So,
no, it's fine. We got the fix, so now you know for future classes.
Yeah, because okay. All right, now, yeah, and I hadn't even heard of a spotlighting feature in Teams, so okay. Love how virtual teaching just makes things easier, doesn't it? And never adds complications. Okay, so the example from last time was b of x, ux, x is equal to 0, where b of x is equal to 1 when x is less than 1/2 and 2 if x is greater than or equal to 1/2. And two solutions were discussed. So we have, and this is the one that's derived in the notes. And so I would recommend that you look at the notes. These are posted in Canvas under the discussion item for last class, where I've gone in there and added new details. I mean, the details I discussed in class, but now they're written neatly. So, and it turned out to be like 4/3 x, and then 2/3 x plus 1/3. Oh, boundary conditions. U0 has to be 0, U1 has to be 1. Okay. Right. Now, this solution, as discussed last time, turned out to be weak because it is in C0. It is continuous. Like if you plug in x equals 1/2, then then they agree. However, the derivatives are 4/3 for one piece, 2/3 for the other, so it is not in C1. It is not continuously differentiable. But this is a second order PDE. A classical solution would have to be twice continuously differentiable. This isn't even once, so that's why it's weak. Okay, so that was one solution. And then I discussed another possible solution. This u of x equals x. Now, a polynomial, not piecewise polynomial, this plain polynomial, is always C infinity. It has derivatives continuous of all orders, because those are also polynomials, or 0. So the question becomes, is this not a classical solution? Because there are two properties that a classical solution needs to have. One, it has to have enough continuous derivatives. This certainly does. And of course, it has to be a solution of a PDE. And that's where the problem lies. And this is what I did not get into last time. So why is it not really a solution of a PDE? Because so why is that? Because in this case, b of x ux, well, the u dx is just going to be 1. So it's just going to be b of x. Okay. But then, what do you do with b of x ux? Take a derivative with respect to x. Not differentiable. So when you try to substitute x, u of x equals x, into the PDE to check it as a solution, find you can't actually do that. That's why this PDE does not have a classical solution. On the other hand, this one, if I take b of x ux, I work out this part inside, which is constant. You can take the derivative everywhere. Here you can take a derivative at every point except at 1/2. That makes the whole thing fall apart. So you need to be able to actually substitute a solution in cleanly and have all derivatives exist as you carry out substitution. Otherwise, it's not a solution at all, let alone classical or weak. You don't even get that far. So I want to try to, I felt like this was not really resolved last time because I was doing things on the fly, which always leaves things unresolved. And so I wanted to make sure that this was discussed completely so that you can see the distinction between classical versus weak. Any questions about this rather kooky example that admittedly has nothing to do with numerical methods? Okay. Now, one more thing about classical versus weak. I have one more example that should be really quick. Before moving on to another section. And this is a particularly interesting equation. And this is called Berger's equation. I should mention that one of my papers from 2 years ago, I kind of embarrassed by the reviewer. He didn't write Berger's equation like this. He wrote Berger apostrophe S. And the reviewer said, no, it's this. So the guy is not Berger. He's Berger's. So that's what the equation is. So the equation is ut plus 1/2 u squared derivative with respect to x of the whole thing But that could be written as, if you were to actually work out the derivative using like the power rule and chain rule, you would get UUX is 0. So this is conservation law form. When it's written as derivative of something with respect to t plus something with respect to x is 0 as a conservation law. But what we can see, because it's u times ux, this is what's called a quasi-linear PDE. Okay. Now, what often happens with nonlinear PDEs like this one is, if you go ahead and try to solve it, that even if your initial data is nice and smooth, eventually the solution will develop with discontinuity. Which is known as a shock. So, because your solution is not even a continuous function eventually, any solution that you have is going to be weak. Now, equations like this one that have that come from conservation laws can be used to model some very interesting phenomena. And one of those equations, may not necessarily be this one, but equations like it, model traffic flow. So when it's traffic flow, the interpretation of a solution is at any particular point along the road, at any particular time, the solution refers to the density of cars at that point in space and time. So what ends up happening is, as you have like more people getting on the highway and rush hour traffic, and the road starts clogging up, then mathematically what's happening is the solution is developing a discontinuity. The solution is getting steeper and steeper. That you're having this sharp change in the density from one point to the next. And so then the natural question is, if you're modeling traffic flow, what does that actually mean physically? What's actually happening on the road that corresponds to a solution to a PDE developing a discontinuity? And this is something that I've actually experienced in large cities like Houston or LA. Probably wouldn't see it around here, no matter how annoying Hardy Street can be. And 59 doesn't really develop enough traffic to show those times. But so I don't know if you've ever experienced like this like in a larger city, where going along like on an interstate, and traffic's moving along pretty well. There's a fair amount of traffic, but you're able to go like 65. And then all of a sudden, everything slows down to a crawl. And there seems to be no identifiable reason for it. There's not an accident, nothing like that. Everything just slows down, and everybody's like, why? What the hell? Why are we not moving all of a sudden? We're moving just fine. And then, so what happens in that case is the density keeps increasing as more and more people are getting on and reaches the peak, and then people are not able to move. It just gets too clogged up. But then sometime after that, people are still moving, like ahead of that location, and so there's a steep drop off in density. Like people who manage to not get caught in that logjam. And then after we're stopped for a while, unable to move, then we start moving again. And something kind of freaky happens because, like for instance, when we stop at a red light, you're several cars back. Light turns green. And then you have to wait a long time before you can get going, even though people ahead of you are already moving. That's because information travels at a finite speed in equations like this, where they have a ux term, it's advection, finite speed of information travel. So that's why you gotta wait. If this was if traffic flow was described by a diffusive equation, like a heat equation, then you'd be able to move immediately when the light turned green, even if you're far back. Unfortunately, nature doesn't work that way. So what happens is, after everybody's slowed down to a crawl for some strange reason, then we start moving again, but in lockstep. So different behavior than what you observe from a red light turning green. They're all going to move along at a uniform speed. And if you were to compare this to a graph of a solution in a situation like this, it develops this continuity, and then after this continuity, the wave keeps propagating at a uniform speed. And a few years ago, when I was on a road trip and I was passing through Houston around rush hour in the evening, I actually experienced that. It's like, okay, moving along, stopped, and then we keep moving at this uniform speed. It's like, that's exactly how the mathematical solution behaves. And that was like the coolest thing ever. So I just wanted to share that PDEs are real. So I guess you can debate about whether it's art imitating life or vice versa, or in this case, math is art. But so that kind of behavior mathematically is represented as a discontinuity, and that's why we only have a weak solution. But I thought I'd use this time to. This class is going to be even more full of digressions than other classes you've had with me. It's just that kind of class. Because we only really get to scratch the surface of PDEs, but I want to try to cover as much as we can. Still don't know what's going on with Samson. He hasn't, haven't heard from him, so.
It's Monday. I almost did that.
Oh. Okay, well, that's going to be extra interesting because I meet with him on Wednesdays. So will he think it's Tuesday, or will he realize like, oh, okay. So at some point there's going to be a realization, and I hope I'm ready for it because that'd be funny. Sorry, Samson, you're not here. I had to. Okay, so that's all I have to say about classical versus weak solutions. But if solutions like this that develop this continuity are a huge headache for numerical methods, because numerical methods are generally designed to work with smooth functions. And that's mostly what we'll deal with in this class. But maybe we should do a sequel class on equations that are more difficult. Are there any questions about anything on this board before I get rid of it? Okay. Now, there better be an eraser here. This next section actually relates to the very first homework problem. So you'll be able to get started on that. So what time is it? Almost 3 o'clock. Okay. Okay, 1, 2, 3, 4, 1, 2, 3, 4, 5. Okay, this is 1.5 in the notes PDF. All right, Fourier methods. So Fourier series, which you would have seen in other classes, for example, 517 or 606, are great for solving PDEs, also analyzing the behavior solutions of PDEs, because they lend themselves so nicely to differentiation. Now, we look at what are called IVPs, or initial value problems. Okay. We'll also see later initial IBVPs, initial boundary value problems. But in this case, we're not going to worry about boundary conditions, such as initial value problems. So they're time dependent. So we have UT equals UX, that is advection. So the solution of this is a propagating wave in one direction. UT is UXX, so that is diffusion. So you recognize this as a heat equation, where a solution does exhibit diffusion. Okay, and then let's just keep going with the spatial derivative. UT equals UXXX. That is called Airy's equation. And then one more, UT equals UXXXX. That doesn't, I'm not going to give that a name, and you'll understand why a little bit later. One equation I showed before was UTT equals UXXXX. That's a beam equation, but here we're just having a first derivative with respect to time. Okay. Now, and for us, we're going to consider these equations. A spatial domain is just the entire real line, so no boundary. Another term for that you may have heard is a Cauchy problem. So when the spatial domain for PDE is just minus infinity to infinity, that's called a Cauchy problem. All right. Now, okay. Oh. Okay, that's weird. Oh. Sorry. I need to talk about two cases here. If we're on a entire real line, which is a Cauchy problem, then the way that we would solve this problem is using what's called the continuous Fourier transform. Okay. So what is a continuous Fourier transform? We have, okay. So we express the solution, u of xt, as an integral e to the I omega x u hat omega t d omega. This is omega, not a w. Okay. Where u hat of omega t is defined to be 1 over 2 pi, similar integral, still minus infinity to infinity, e to the minus I omega x, u of xt dx. So notice this is with respect to x integral, here we're integrating the other integral with respect to omega. So this is the Fourier transform. And this is the inverse transform. So Fourier transform takes a function of x, which is defined in physical space, and gives you a new function of omega, and in this case, t just tags along for a ride. And this function lives in what is called frequency space, also known as Fourier space. Well, I think frequency space is more descriptive. So you can think of the variable omega, the Fourier variable, as a frequency. Okay. So that's a situation where we have a when the problem's finding the whole real number line. But what if it's not? What if we are on a finite interval? Okay. So if we're on the interval, say, minus pi to pi, and periodic boundary conditions. That's actually why, notice I have a parenthesis here for right side. The pi is not included, whereas minus pi is. That's because of periodicity. The value at pi is the value at minus pi, so we don't need it. We use a discrete as opposed to continuous Fourier transform, which is similar in appearance to the continuous one. So what we get there is, check my definitions here. Okay. So this time u of xt is a sum instead of an integral, but it's an infinite sum. So this is where we get continuous versus discrete. All right, so we have uk hat of t e to the ikx. So notice the same kind of complex exponential. Here we have a coefficient that depends on the Fourier variable k instead of omega, and still for the function of t. And these coefficients are still defined as an integral that only has one difference. It's on a bounded interval from minus pi to pi. So whatever spatial domain you have, that's what your Fourier transform integrates over. That's e to the minus ikx u of xt. All right, so that's the discrete Fourier transform, which I'll be working with in the rest of the section. Okay. And did anyone tell me what is the term for this? I know everyone here has seen it before in another class, well, 517, or at least you took 606. What do we call this? This way of expressing u of xt? Forgotten everything? Fourier series. That's what this whole thing is, this way of expressing the solution. Okay. depends on what spatial domain you're dealing with. Okay. Even though we started late, I still want to have a break in the middle, so it's a good time for that. And then I'll show why Fourier transform is so helpful for solving PDEs like these. Well, I guess you can all talk among yourself, those who are here in the room and those who are virtual. So, I'm going to immortalize on YouTube, or I can mute them and or mute myself so that doesn't get recorded. Then some of you can't hear each other. So I don't know.
YouTube for calculus. Yeah. Like
Yes.
this week.
Yes.
Yeah, I did. It's 2 today, and they both said limits, and I'm like, no, my limits, but I haven't had a refresher in a while. So that'll be interesting. Hopefully, it's in person now, so hopefully they'll bring their stuff.
I had a guy Friday who came and asked about saying he was confused because his teacher had just introduced the concept of limits the the day before. I was like, basically, here's what you're looking at. I don't want to go super in depth because she's just introducing the topic. There's a lot more she's going to go bring across about it.
Step two.
It was for one of the, it was like, it was like for 102 or something like that, one of the applied calculus classes.
Oh, yeah, both of mine went for the class. Who knows?
I have a calculus who signed up for later this week.
It'll be fun. I forgot that I do other things in 101. I told somebody messaged me saying, I need to cancel my appointment. I have to get testing for COVID. I was like, no worries, just go cancel it. And he was like, can you do it for me? I don't know how. How do we can schedule the appointment?
Like, just click on the box that you signed up for and you cancel. It's not that complicated.
Yeah.
Okay. You wouldn't think that ordinary in-person teaching at the board like this would be physically taxing, but I discovered last week that when it's 3 classes in a row, and after over a year of only virtual teaching, it kind of is. The contrast really hit home. I mean, well, I know you were in-person teaching last year, were you? Okay, yeah, so it hasn't changed that much, but yeah, like, oh my God. So I'm gonna be toast after I finish 560. Okay, now, sticking with the case of a PDE defined on a bounded interval, using a discrete Fourier transform. So now all the PDEs that I listed earlier all have the same form. They can all be written this way. There'll be a partial derivative of order n. So I'm just writing this way, where n is equal to 1, 2, 3, or 4. Now, if you replace u by its Fourier series that I wrote earlier, sum over k minus k to infinity, u k hat of t e to the I kx. So this is relatively simple to substitute into the PDE because we have to take derivatives with respect to t and x, but each term is a product of a function of only t, the function of only x. So I substitute in okay, so what we get is following. You pull out the sums over k, and we're going to have now, what happens when we differentiate this with respect to t or x? With respect to t, we're only going to take the derivative of this factor here. So it's going to be derivative of uk hat of t with respect to t, and this part is unchanged. Then, when we take a derivative with respect to x, well, this part's get left alone. I differentiate this with respect to x. What happens when I take a derivative of that with respect to x? Yeah, so each differentiation with respect to x gives a factor of ik. And because it's a derivative, we have ik to the n. UK hat of t. So, in both cases, this factor of e to the ikx is still there. Because when you take a derivative of an exponential, that exponential is the exponential times something. So I factored it out. So now, from a PDE, we have this equation. Is everyone good about how we got that equation before I continue with it? Now, these functions, e to the ikx, if I get a linear algebra on you, they're linearly independent. So you can think of this as a linear combination of linearly independent functions equaling 0. By definition of linear independence, the only way that can happen is that the coefficients themselves must all be 0. So, from our PDE, by taking the discrete Fourier transform, I should make it clear that we're on this spatial domain. Okay. For our PDE, we now have a family of ODEs that must be satisfied. So, derivative of UK hat is the function of only t. With respect to t must be ik to the n, UK hat of t. So we have a one parameter family of ODEs. That parameter is k. All right. Now, this is an ODE that's particularly easy to solve. But I'm not going to take the time to put you guys in a spot to dredge up your memory of your first ODE class, because it may have been a while ago. But if you don't remember, hopefully this jogs your memory a little bit. So, because we have this constant here, we can have an exponential, ik to the n times t times the initial value, UK hat of 0, which would come from the initial data for your PDE. I'll just write that out. So we take a discrete Fourier transform of your initial data. So u of x0 is prescribed to be u naught of x. Okay. So now that I've solved these ODEs, I've solved for the Fourier series coefficients. In other words, I have these now. Now I can write down my solution for these different PDEs. So I have Fourier coefficient of initial data times e to the ikx plus ik all to the n times t. So questions about how this solution was obtained? That's one of the things to have burned into your brain is this ODE comes up so often. Y prime is a constant times itself. That's the solution to the AT times the initial value. So that's just what I was using to solve for UK hat of t. Okay. All right. So now that we have this for n equals 1, 2, 3, 4, let's find out what can we learn from this solution formula about how the solution actually behaves. Where we consider the cases n equals 1, 2, 3, 4 separately. It looks like I can get myself right back on schedule, since after Tuesday, I'd accidentally gone ahead, but some nicely unplanned digressions have knocked me behind to be back on time. So. Okay, so okay, so first we'll look at n equals 1. So advection. UK hat of 0. Then I have e to the, I have ikx plus ikt. So I'll just factor out ik. Now I have that. All right. Now, I contrast this with the initial data. That's u naught of x. Well, that's going to look much the same because set t equals 0. It's just this Fourier series. Okay. So with the two side by side, or okay, one on top of the other. How do the two relate to one another? Like the fact that this x here becomes x plus t. So if you have f of x versus f of x plus t, how do the two functions relate? Oh, let me put it this way. Suppose you have a graph of f of x. How do you quickly obtain the graph of f of x plus t? Really, I could write this way. It's u naught of x plus t. I don't know if they still teach this in Math 101, but it is some pre-calculus-y thing. But graph transformations? Anyone?
Would it just be shifted to the right by however much t is?
Close.
No, it's plus, they're shifted to the left.
Yes, when it's plus, it's to the left. When it's minus, it's to the right. So, yeah, so that's what u of xt is. It's just a graph of u naught of x shifted to the left. So, so what we have here is propagation to the left, and the speed is equal to 1. Now, where do I get the speed? When I write the solution this way, the coefficient of t is the wave speed. So if I had instead du dt is equal to 2 du dx, then I would have a wave speed of 2. I'd have u naught of x plus 2t in that case. All right. Okay. That's a question about this case before we move to the next. Higher level math is just things from lower level math coming back to haunt you, except you have to contend with all of them at once. Okay. So that's n equals 1. Let's look at n equals 2. All right, so now we have xt is the sum you have k of 0, e to the I kx, e to the, so now you have ik, the whole thing squared. So that's e to the minus k squared t. So what happens is, actually, if you think of this solution as a sum of waves of varying frequencies, so if a frequency is k, the amplitude of each wave comes from this, the absolute value of this, that's the amplitude of the initial data, times this factor here. So the wave that corresponds to frequency k is the absolute value of uk hat of 0, that could be a complex number, times e to the minus k squared t. Okay. So what happens to that, has this amplitude? So what happens to the amplitude as time moves forward?
It's smaller.
Yes, these are decaying exponentials. So this goes to 0. As t goes to infinity, especially for larger k, then that decay is going to be even faster. So the consequence of this is we have a smooth solution. Because smooth functions, the Fourier series coefficients corresponding to larger k are smaller, possibly 0. And here in this case, they go to 0 particularly fast. So if you were plotting the solution over time, even if the initial data was nasty, like really oscillatory, as you plot the solution for increasing time, you see it smooth out, eventually go away entirely. It would decay to 0. Or actually, no, it would decay to a constant. Because for k equals 0, that part will stick around, because this factor would be 1. And that's what you expect from a heat equation, that regardless of what heat source you have that's influencing a temperature at the beginning, if there's no additional external effects over time, the temperature in the room will converge to an ambient temperature throughout the spatial domain. It'll just diffuse to a constant. So physically, that makes sense. So when it's the second derivative, uxx, that's diffusion, we have this exponential decay happening here. All right. Make sure to talk about n equals 3 and n equals 4. Keep most of this. All right, so for n equals 3, we now have the quantity ik cubed. So the way you can write that is e to the ikx, and then, okay, actually, x minus k squared t, because when you take ik, the whole thing cubed, that's equal to minus I k cubed. So that leads to the minus right here. And we have k cubed. I put k out here because both these parts have a k in them. I factor that out. So I'm factoring out whatever I can. So originally this was ikx minus ik cubed t, and then the other two factors of k I leave in here. So this looks somewhat like the case of n equals 1. However, in the case of n equals 1, we just had x plus t. But now the coefficient of t depends on k. So if we were to try to think of this as a graph transformation, what sort of graph transformation would we have now? So e to the ikx now becomes this. So from a graph transformation point of view, if x is replaced by this, yes. So we have propagation to the right, and the speed, so the right is because of a minus, the speed is k squared. So unlike before, at n equals 1, your initial data is a collection of waves, the sum of waves, and they're all moving to the left at constant speed. Here, the waves are propagating to the right, but each wave for frequency k has a different speed. The higher frequency is, faster it's moving. So this is not advection, it is dispersion. So that's what, so when you have PDEs with third derivatives with respect to x, that's the kind of effect that can introduce into a solution is dispersion, because the waves are not going away, but there's a scattering effect. That if your wave consists of both low and high frequency components, smooth parts, also oscillatory parts, the oscillatory parts, they're off to races, they're gone. They're leaving the smooth parts behind. Okay, so now we see mathematically what does advection look like, n equals 1, diffusion, n equals 2, dispersion, n equals 3. So when mathematicians throw these terms out there to make it seem like they know anything about physics, that's what they're really referring to. And yes, I am totally guilty of that because I should be good at physics, I'm just not. I tried, I really did. Okay. Now, finally, something I have a certain amount of shame about. All right, n equal 4. We'll have this case. It's somewhat similar to the case of n equals 2, because you have raising ik to an even power. The result is going to be real. Now you have e to the ikx, like before. And then you have e to the k to the 4th t. So what happens to the waves? Again, so think of the sum of waves to each of frequency k. What happens to the waves in this case? Might be easiest to contrast with the n equals 2 case.
It moves to the left at speed k to the 4th.
No. So the reason why it's not motion or propagation is for the t part, no I. You know, I that you can pull out to think of this as a propagation situation. That's why it's best to contrast with n equals 2. Yes, you would. Because here we had the minus that led to exponential decay. Here it's real. So it's just multiplying the amplitude. Same thing over here. This is another factor in the amplitude. Oh, that should be a 0. Oops. Okay. But because there's no minus here, there's a exponential growth. So what that means is, and this is why I did not actually give a PDE a name. This is an ill-posed problem. This solution does not depend continuously on the data. It's like the backward heat equation. Here, this is a regular heat equation. If this is a backward heat equation, again, there'd be no minus. That's even worse because you have k to the 4th versus k squared. But either way, a tiny change in initial data would result in a gargantuan change in the solution because this factor can get as large as it wants. So we just don't bother with that kind of PDE. It would not correspond to anything physical. Okay. No. All right, so now we've seen a number of cases. So now as far as how you would analyze PDEs more generally, I'll run out of time. Okay, so in general, if we assume that our solution has this form, e to the ikx minus iw t. It's a w, not an omega. Or this is unknown. So the idea is you substitute this into the PDE and you find w so that the PDE is satisfied. Now, this doesn't always work, but if it's a PDE like the ones we've just been doing, especially ones that have constant coefficients, then this is effective. You'll be able to solve for W. Okay. So W will generally be a function of K. This will depend on this K here. Is what's called the dispersion relation. So what kind of dispersion relation you get gives you an indication of how the solution of a PDE is going to behave. And what you also get is the growth factor. In other words, how the amplitude of each wave changes over time is the absolute value e to the minus I W of K. So here, remember, W is a function of K, so that's how I'm writing it here. So as time moves forward, the amplitude of your initial wave, UK hat of 0, absolute value, is multiplied by this. So you'd like to have a growth factor that is not going off to infinity. That would be an ill-posed problem. Okay, so examples. Sorry, I know I'm going over a bit. Of dispersion relations. So, well, I have a whole list that's in the notes. I'll just do select ones. Wave equation. UTT is c squared uxx, where c is the wave speed. So if you assume that the solution has this form, and you substitute it in here and you solve for W, I'll just tell you what the solution is, but you can try yourself and verify. W turns out to be plus or minus CK. And the growth factor is absolute value e to the minus I plus or minus CK T. And all of this is real. So it's e to the minus I times something. That has absolute value 1. That's what we like to see. The waves do not grow over time. They keep their amplitude. Whereas the heat equation, so UT is equal to the diffusion coefficient D times UXX. So if you solve for W in that case, you get W is minus IDK squared. So the growth factor that you get is e to the minus I something seems weird here. I feel like something's not working out the way it should. Oh wait, actually it is fine. T minus I times minus I is minus 1. This goes to 0 as t goes to infinity. So you don't have growth, you have decay in that case. And okay. Whereas like for the area equation, you get W is equal to K cubed. The growth factor is still 1 in that case. So there's other ones in the notes. There's like 9 PDEs in there. Oh wait, no, there's only 5. Okay. My chart is a little off, but generally for a well-posed problem, your growth factor will be less than or equal to 1. Questions about that? So the first homework problem, the only one that's non-MATLAB, you can take a look at. So if you want to get going on that, when you do, then that's something we can talk about in class, any difficulties. As from prior instances of this class, it's a bit of a pain, but because you have a rather unusual PDE to try this out on, to figure out what the dispersion relation is, and so forth, and how the solution can behave. But so, okay, what I would recommend is go ahead and substitute that into these PDEs and confirm that this is what you get for W. Just so you have an idea of going through motions of finding out the dispersion relation of a PDE. Okay, so I went 5 minutes over. The compensate for roughly 10 minutes starting late. So, try not to do that again, but okay, so well, see y'all Thursday, and hopefully all.
Bye-bye, Dr. Burns.
Yeah, see ya.